So, very good. So let's continue. The next speaker is Eduardo Gundelmann, and with a long title on non-Riemannian metric dependence and so on and so on. Please, Eduardo.
Okay, thank you very much. Okay, so I'm very thankful for the invitation, Claudio and Felix, and actually I'm going to talk about non-Riemannian measure independent measures, and this is very much related to the measuring causal fermion system, for example. One can go in one direction, and then there are other directions that okay, so let's see what we do, right? So we're going to review on proposals and consequences of using non-Riemannian metric independent measures of integration, application to cosmology, construction of dynamical tension in string theory, the well-known unimodular theory. There is a nice poster, right, in this here, right? And this is an example of this use of alternative measures, right, concerning application on cosmology, unified description of dark energy, dark matter, and all kinds of things. Well, I'm not going to go through all of this, but okay, you see a long distance, a long set of applications. Let's see. Okay. How do I go to
The other one.
the other button? Here? Oh, here, okay, so. Okay, so how is the measure affecting us from the beginning in cosmology, right? And in particle physics, for example, this issue of the you know in normal physics, Newtonian physics, if you change the Lagrangian by a constant, it doesn't affect the physics. In gravitational theory, however, the Lagrangian is multiplied by this measure square root of minus g. So if you change square root of minus g, but if you change Lagrangian of matter by a constant, this will induce a cosmological constant term. So it's the measure seems to fail already from the beginning, at least in connection with the cosmological constant problem, right? So this shift is problematic, right? So the way we go and address this problem is to change the integration measure, right? Integration measure. And the integration, we define this antisymmetric tensor field here, contracted with this, right? And then this gives us a, what do you call it? Okay. Yeah, so the first normal measure, right, is constructed with the square root of minus g, which can be expressed in terms of Weerbanes as determinant of the Weerbanes, right, something like this. So this is the measure that is a normal measure, right? Now we can do something more general and then consider a antisymmetric tensor contracted with right, and then consider the curl of this antisymmetric tensor, and this is it becomes a total derivative, right? And in this case, we can also generalize in a more, for example, consider the normal measure, right? Or one of the measures that couples to curvature and some Lagrangian, and other measures that couples to a different Lagrangians, and all of these are total derivatives. So if you vary with total derivatives, you get that all these Lagrangians here have zero derivative, right? All of these. So you get a set of Lagrangians that are equal to 0. Now we remember talk by Felix, right? He said constrain that the d rho equals to constant, right? Now we say this d rho we identified here as some divergence of something, right? D for x, right? This is the d rho. This by Gauss's theorem, this becomes the h mu d sigma mu. So this will be like goes into this volume element. It goes into the something that goes into the boundary. But in the variational principle, you don't change the boundary. So this is the same as saying that in the variational principle is a constant. So it's a very good fit for an effective theory that comes from a causal system, right? So we have worked all these kinds of theories, for example, and we see that the ratio of a measure, for example, becomes, if we use the second order formalism, this becomes a dynamical field and it satisfies some equations of motions like this, right? And now we have a famous theories that are particular cases of this, right? Something like that. So one of the famous theories that is a unimodular theory. When you use the unimodular theory, when you the original unimodular formulation violates general covariant invariance, but you can formulate it in a general covariant invariant way by using this phi. Now from our point of view, this is a modified measure, right? Something like this. It's a divergence of some f mu, and the f mu is the dual of this vector that I use. There is a nice poster here. Now about using this, right? So if you vary with respect to lambda, you get that this measure is equal to square root of minus g. And if you vary with respect to lambda, you get that, and this is the square root of minus g. And the rest, you vary with respect to g mu, you get the Einstein equations, okay? And the variation with respect to the measure says that this Lagrangian, which is L, is a constant. So the cosmological constant becomes a floating variable, right? And if you look in the poster that we have here, the F0 can be used as a time variable. And this is a general feature that we have used, this measure fields, if you want, you can find the time there. That's the alternative that the coordinate time, and there is a nice use speculation that this provides a nice application for the solution of time problem in quantum cosmology. Okay, another famous model that is very nicely fits into one corner of the modified measure theory is the Jakob-Teitelbaum theory. In 2 dimensions, if you go to 2 dimensions, there is no gravity, no Einstein gravity. But you can put the measure here and couple to curvature. And the measure, this variation with respect to the measure tells you that the Lagrangian, which is curvature, is equal to a constant. That's it, right? And it gives you exactly the Jakob-Teitelbaum theory. So this is another example of some kind of well-known theory that fits in one particular corner of the modified measure theory. Yeah. Okay. How do you do this? How do you see that the modified measure can be used in terms of Lagrange multipliers? Right? If you understood with Lagrange, without explicitly putting this, that this is the divergence of something, right? You put this measure here, You treat the measure as an independent variable, right? An independent density, as multiplied by this, multiplied by the measure, multiplied by this. And then you constrain the integral of the measure to be a constant, like Felix said, or something like that. And then you vary with respect to this Lagrange multiplier, which is a number, right? And then you get that this equals to a constant, this volume is equal to a constant, this other volume is equal to a constant. And then you vary with respect to the measure, and then you get that this Lagrangian equals to this constant, this Lagrangian equals to this several constant, right? Something like that. So this is what I said. This is what you get from the variation of the measure now, right? And the variation of the, yeah. I was talking with Witten in Princeton about this modified measure, and he told me, oh, but this is exactly what Perelman did. This is the action, central charge action of Perelman. He takes some kind of a volume, fixes to 1, because he has a similar problem that Felix says, that if you don't fix this volume, this integral of measure to be fixed, everything collapses. So Perelman had the same problem in this Perelman entropy action for RG flow. So this is interesting to compare with the causal Fermat system, modified measures, Perelman action. Okay. So as we say, this measure automatically satisfies the first action of causal Fermat system. We have written a paper that is in the bottom, right? Is with Claudio and Felix, right? As modified measures as effective theory for causal Fermat system. Okay, then other applications, right? A model of unified dark energy, dark matter. You use some kind of a square root of G, some coupled to curvature, X, right? The kinetic term of a scalar field, and this in this way. You reorganize these terms, you can put this in this way. You get some constraints, yeah. Then you get some divergence of a certain current, right? You write the energy momentum tensor, becomes like an energy momentum tensor of dust and dark energy, right? The velocity, the Fock velocity is defined this way, satisfies that. The energy density, this integration constant enters into the dark energy constant, right? And then you have a geodesic motion. You can show this geodesic motion. For u equals 0, you have a symmetry, because you see you have a conservation law. And yeah, the symmetry is related to this. So the exact dust behavior is related to a symmetry. Okay. So now models with scale invariance, right? And avoidance of Fish force. So you have, right, you have a scale invariance, global scale invariance. The gamma moves are invariant. The scalar field is shifted, and the measure is shifted, right? So you have integration of the curvature involving both terms, right? And then you have kinetic terms coupling to both measures, potentials coupled to both measures, and the Lagrangian of matter that appears here is coupled to both measures, something like that. You define the density, well, whatever. Density of particles, right? It's like a set of particles that are staying there in some places, right? Static, for example, to see what's happening with this theory. The Lagrangian of matter is this. You go with what's called the Einstein frame, where the connection becomes the Christoffel connection, right? You look at the density, effective density of matter, and then you get the effective Einstein equation of motion, right? Whatever. And then you see that there is a equation of motion where the dust has produces some energy density, right? Something like that. Because this is the energy density produced by the scalar field. That's not so norm. But then the dust here is producing a scalar energy density. And also a dust is producing some pressure. So this is an anomalous behavior. But then there is dust is the source also of matter, right? So the matter, the scalar field is coupled to the density of matter. But then there is a constraint that tells you that if you go to high densities, this combination here has to become zero. So in order to satisfy this constraint, this is something that goes to the vacuum energy of matter of the universe, and this is so you have to set this to zero. And if you set this to zero, the pressure, the energy density from the dust, right? The energy density is okay. The dust can have energy density, but no normal dust will produce pressure. But this combination is exactly zero, right? And the matter is decoupling from the dust if this constraint is satisfied, right? That this is zero. So, okay, so this is a solution of a Fish-Force problem. I don't go into detail. Okay, this is too much of detail. Yeah, you can apply to models of inflation, right? Using all kinds of things. You can get the K-essence models, right? Something like this. You can solve from the constraints, the ratio between the two measures. You have a potential of this sort that satisfies inflation. You can have actions that somehow incorporate square root of minus g. Yeah, because you introduce another field phi that constrain this measure to be proportional to square root of minus g, right? Chi2. Yeah, and then we do all kinds of actions, right? Yeah, we can put Higgs fields and all kinds of things, right? And we have a model, a potential with a Higgs field, and if phi goes to infinity, you have like exactly the normal Higgs fields that, right? And if phi goes to minus infinity, you get exactly a constant, right? This divided by this, right? Something like that. Okay. So all kinds of application. There is yeah. So this kind, we have models like that with inflation, right? Inflation here, right? And then goes to dark energy, right? Something like this. And so we work in models of this sort with R square also. The R square is coupled to this, what is it? Yeah, well, R square. And then we take two scalar field model, right? Something like this. And just with the exponential potentials, this integration constants break from you the scale invariance, right? I just show the picture. So you have actually a model like we have inflation and dark energy, and yeah, it's actually a model that shows three sectors for dark energy. Dark energy, inflation, early dark energy, and late dark energy, right? Something like this. So we show here One limit is has the inflation. The other limit is dark energy. The other early dark energy, late dark energy, right? Just go through this because I want to show a lot of stuff. So, okay, we solve all this. We have also K essence and the different limits. You have also the possibility of having all kind of, I just show a lot of models that we have here. The other application is to have a holomorphic theory, because you see another problem with the square root of minus g is that the square root of minus g is not holomorphic. So you can avoid the square root of minus g by introducing a constraint omega square minus g equals a constant, and this, when you solve this constraint, you get the measure square root of minus g, but then you have two branches. But then the theory in itself is holomorphic, but it is spontaneously broken by and then you get to the square root of minus g. Okay, and there is another representation of this measure with the four scalar fields, right? Something like this. And the determinant of Jacobian of four scalar fields to space-time, it gives you integration of four scalar fields, right? Yeah, and then this is the holomorphic theory in terms of these four scalar fields, right? Now, the last application I wanted to discuss is a application to a string theory. The string theory has, of course, uses the Polyakov action, right, where you have the square root of minus g. Now you replace the square root of minus g, square root of minus gamma by a measure, right? This is a total derivative also, and then you have two scalar fields, right, something like this. In order to have a consistent theory, you have to introduce gauge fields that live in the brain. So if you vary with respect to this, the fields in the measure, you have like a derivative, something here, the derivative, something, the derivative of the Lagrangian equals 0. If the measure is non-singular, you get this Lagrangian is equal to m. Equation of motion with respect to gamma IB gives you this, right? You can solve for this object that appears here by taking the trace and put here, and then consistency tells you that this m equals 0. And the interesting equation is that the ratio of these two measures is, derivative ratio of these two measures is 0. So the tension of the string becomes an integration constant, right? Something like this. Now you introduce currents to have the more dynamical theory, right? You have J mu, and then you introduce a scalar field, which is the tension field. And then you project the derivative of this tension field onto the worksheet. And then you see that the integration constant, the tension is not anymore integration constant. It's each tension, each string can have its own integration constant, but then the measure is equal to this, right? Something like that. Yeah. So each string generates by itself and so you can have two. Doesn't mean that there is one string with this integration and all of them because the string can reproduce themselves, right, by their interactions. So you can write the action for a certain string with this, right? So you see that there's the other terms that are background fields that are introduced. We keep them. But you see that there is a embedding space string of the strings I has to satisfy Einstein equation. If we say that these fields, additional fields are trivial. So the fields I, for example, you have 1 and 2, the Armonu, the Einstein equation are this, and the Einstein equation for the string 2 are this. So there are two Einstein equations for conformally related metrics. It's not trivial because Einstein equations are not conformal invariants, right? So, but the string metrics are related by a conformal transformation that we can call omega square, right? From this equation, 117, we can get the phi, and then the string tensions are related into this way. And we can take, for example, two measures, two strings that are, this is one example, right? That are related by, one is Minkowski space and the other is Minkowski space after special conformal transformation. You see the omega is this, right? A mu is a D vector, right? Is a D, for example, is equal to 26, right? And then we can look at the tensions, right? The tensions are like this and like that. And in some limit, A goes to 0 and T2 minus T2 equals 0. The strings are equal, so you get some tension like that, right? The metric coincides. Let's see. The two tensions they are equal for a long time. If they have the T2 minus T1 is small, then afterwards they become two surfaces separated, right? The two surfaces are living at this point and at this point. And at those points, the string tensions become infinite. So the tension, this becomes like a brane world scenario, right? And to be short, right, these surfaces are like hyperbolic surfaces, right? And everything goes into one of these is constant. The two surfaces become infinitely close, right? And at these surfaces, right, one of these surfaces, for example, is like this, and you can see that this surface is like that, and this is if you go to Euclidean space, it goes a plus, so you have like a universe creation from nothing, right? If you look at the Euclidean sector and then creation of the universe, right? And of a brane world universe, right? Everything, it becomes close to this surface. Okay, and well, I say that if you look at this model doesn't have the tension goes to infinity. It means that because the Hagedorn temperature, for example, is related to string tension, and the string tension goes to infinity. At the end, you'll see, for example, that the other constraints, the Swampland go away because the Planck mass is dynamical. The string tension is dynamical, the Planck mass is dynamical, and all the string Swampland constraint, this like M Planck is dynamical and become very big. So this is meaningless. This Swampland constraint also, if this is bigger than something, but is multiplied by something very, very big, it becomes meaningless. The last paper I wrote is the dynamical tensions. Well, the dynamical tensions go to infinity. It means the Planck scale goes to infinity. And the last idea I was writing is that I was talking to also with Maldacena in my same visit to Princeton, and he told me, "Oh, you are doing a string tension with different string with different tension. Ordinary string tensions, ordinary string interaction decouple if strings have a different tension because the string splits and then produces other strings with the same string. So I thought that this is interesting because this gives me a possibility of postulating that the dark matter are strings with a different tension. The baryonic dark matter, 3 minutes, okay, just on time. So the baryonic dark matter or the standard model dark matter are strings with certain strings, and the dark matter are strings with the other dark matter. And according to what Juan told me, they will not interact. They only will possibly interact through this new tension field that I introduced, right? And so this was just the paper I wrote a few just last week, and then there was already in Science magazine some comments on this, and the previous paper that I mentioned about the avoidance of swampland has a lot of comments in the social media and all that stuff. And so the other things that we have been discussing with my colleague Douglas Singleton, the string tension appears in the non-commutativity of the coordinates, and then it enters in the vacuum energy, right? So in the 0 point energy depends on the non-commutative coordinates. So the vacuum energy becomes dynamical, and this is not finished work. This is being done with Douglas Singleton. Okay, so that's more or less. Thank you very much.